ridiculous, but all right. So if you come in here and you want to draw your, you didn't know where you were, did you? Oh, no. 11, we're good. Cal 3. So you draw your x-axis coming out this way, right? And then your y-axis would come out this way like this. Z. That makes sense? So let's say you wanted to plot the point 1, 2, 3. So you go out on the x-axis, you go 1. Then on the y-axis is 2, so you'd move out 1 space, 2 spaces. And I'll kind of draw a little rectangle on the ground there. There's where you are. And then you go up 3, right? So you can just follow 1, 2, 3, and that's where you'd be. And I'll come in here with a little box to kind of show you how that kind of looks in three-dimensional space. So you can see the 3D graph paper kind of helps if you're having trouble with drawing in 3D. All right? So feel free to download some of that, print it off if you want. There's not a whole lot of 3D graphing that I'm going to ask you to do. There's not a whole lot of it, but you still want to be comfortable plotting points and things like that. All right. Now, we're not recording? Or are we recording? We're recording. We're going to pause the recording. We're going to do a quiz. All right, so here's the problem worked out. All right, we need to find the center of the sphere first, right? Because we're trying to find the shortest distance from the center of the sphere to the y-axis. So the first thing I need is the center of the sphere. To do that, I have to recognize that I have an equation that to find the center of the sphere, I have to do what? Complete the square, just like in your homework, right? Just like in your homework. You had to do that, complete the square. So we complete the square on all the terms, and you work it out, and then you make it look like the equation for a sphere, and you realize that the center is 1, -3, 4. After you've realized that the center is 1, -3, 4, I went ahead and drew the picture here. If I go on my x-axis out 1, I go y, -3, and I go up 4, I have a point right here. And I kind of drew out the box to kind of help you see which octant it's in, right? What octant is that in? We go this way around, right? So this is 1, this is 2, this is 3, this is 4. So it's in the 4th octant. And we're trying to find the shortest distance between that point and the y-axis, which would be that blue line, right? And I hadn't quite finished it. But if you kind of blow that picture up, what's this distance right here? What's this side of the triangle? It's 1, right? It's that distance right there. So it's 1. And then this height of the triangle right here is what? Is your z coordinate. So that's 4. So that's √17. That's it. Okay? That's one approach. You may have approached it a different way, but that's me trying to show you with as much detail as possible. Any questions? I think that quiz is a good example of if you did your homework, there was not a problem like that. But I think that the concepts in that section, if you kind of have your head around the concepts of that section, you should be able to get to this result from this, this question. Make sense? All right. I just don't want you to, I think I said last time, I don't want you to get the impression that the problems I'll ask you are going to be exactly like what's in the book. There's always going to be some sort of adaptation that you're going to have to understand the fundamentals to be able to solve the question. All right. Any questions on homework? Anything that anyone wants me to discuss? All right. So I'm going to pick up with the notes where we left off last time. We had just finished 10.2.9. And we had said that when you define a vector, these things here, which are usually numbers, are what are called the components of the vector. And the difference, the language was that we call them components as opposed to coordinates. Coordinates we reserve for when we're talking about points, right? So we have 2- and 3-dimensional vectors. And then we stopped and we said, okay, we'll come back. So here's where we are. We're going to look at what's called the parallelogram law for vector addition. So if we have 2 vectors and we want to add them together, we have some rules as to how, what happens when we try and do it. And it turns out that geometrically, when you add 2 vectors together, they create a new vector that when you draw it all out, you get this parallelogram. So let me just show it to you. When we add 2 vectors together in 2- or 3-dimensional space, we take the tail of one vector and paste it to the tip of the other. And it turns out it doesn't matter which one you do. So given 2 vectors in 2- or 3-dimensional space, remember we had if it's pointing it out, right, this way. This was the what and this was the what? This is the tail, that's the tip, right? So I have 2 vectors sitting out here. If I want to add them together, I just take the tail of one and paste it to the tip of the other, or I could have done it the other way. I take the tail of this one and paste it to the tip of that one. Now, you have to keep keep the vector, when you move it, you got to keep it pointing in the same direction as it was originally, but you just have to move it so that the tail and the tips match up, all right? So here's a 2-dimensional picture of that happening. I have a red vector. I have a red vector, which I'm calling V. I have a blue vector, which is U. And if I add the 2 together, I take, take this U here. We take the tail of V and paste it to the tip of U, right? That's the tail of V to the tip of U. So the resultant vector, the result is that you get this new vector right here. So it's kind of like you travel along this path. You start here at the tail of U, up to the tip of U, which is the tail of V, and then you travel down V, and that takes you here. So the result of these 2 vectors being added is this new vector U plus V. So it just goes and points in this direction. Now remember, vectors can be moved around, right? They can be slid wherever you want. So in order to add them together, you must get those tails and tips to match up. Now let me try and see if I can go the other way. Let me try and okay. Is that U plus V? No. That's tail to tail, right? That's not U plus V. We have to get them to, trying to get these to line up. Will this work? If I put those together there? Yes. And so now you can see I'm going and I'm taking V, right? I'm taking its tip and attaching the tail of U to it, and it takes me here. So the result is this new vector. It points in this direction. And that's because we start here at V, travel through, go to U. So the result is just going from here to here. All right? Questions? Where's the whole idea of parallelogram come from? I don't see a parallelogram, do you? Yeah, let me do this. If I come in here and I'm going to draw that vector again, okay, like that. Remember that vector's there, right? Now I'm going to switch and I'm going to move V. No, I'm going to move U over. Let me move U to the right. Okay, you see that vector down there? Okay, I'm going to draw on top of that too. Oh man, what happened? I know, but why did I lose it? When I moved it, I think it scaled the whole damn thing. Screw it. I'm just going to get up here on the board. There. Okay? Can't get it to work. There you go, right? So if you do U plus V or V plus U, depending on how you attach the tail and tip, you create this parallelogram. All right, next. A lot of times in this class, what you'll see when we get to examples that I consider to be somewhat trivial, like this one, I will just kind of direct you as to what you would do, but I won't work through them, and it's kind of left to you to kind of do it on your own. So for something like this, it says use the drawings below of the vectors v, u, and w to sketch the following. So let's just do one of these. What's v plus u? So what I would do is I'd first clear this out. I take v and u, and I want to attach the tail of one to the tip of the other. It doesn't matter which way I do it. So I'm going to take v, and I'm going to move it up. And I remember, I got to keep it pointing in the same direction. I got to move it up, and I'm going to move it over. So if I do that, it should be something like, what do y'all think? About something like that? All right, it's not perfect, but you know, that's what I would have, right? Now the result, u plus v, would be the vector that starts at u and goes to the tip of v. So there it is right there. Remember, ooh, crap. This is v. This is v. This one right here would be u plus v. Right? That one, that little yellow one right there. And then you could do the rest, u plus w, and then add them all. So what would happen if you do three vectors added together? You do tip to tail, just all of them in a row. And again, it wouldn't matter which one you put first. Questions on this or not? All right, now that's how you add vectors geometrically. That's what's happening. But mechanically, when we add vectors, if you're in two-dimensional space and you have two vectors, u and v, each one of them will have two components, right? And to add up the vectors, u plus v, all you do is add the components. So you take the first component of u, you add it to the first component of v, that creates the new first component of their sum. And then you do the same thing with the second components. With the subtraction, it's the same thing with just subtraction between the components. In three-dimensional space, same exact thing, except you have to do it for all three components. So vector addition and subtraction is pretty clean. There's no magic happening here. So right now, up to this point, we know how to add and subtract two vectors, right? Add and subtract. So now let's talk about multiplying, not multiplying two vectors, but what we call scalar multiplication. So what if I take a vector and I multiply it times a number? What does that mean, and what does it do, and what does it look like visually? So given a vector v and a scalar c, so c is just a real number, then multiplying the scalar times the vector changes the shape of v. If the magnitude or absolute value of c is bigger than 1, it's going to stretch it out, make the vector longer. If the absolute value of c is between 0 and 1, it's going to shrink it, make it smaller. If c is negative, it's going to flip it. So it's going to change the direction. It's going to point it in the opposite direction. Further, the way we compute it is if you have v and then you have c and you want to multiply it, you basically distribute the c through the vector to each of the components. So it's just scale it through. And then all these concepts can be extended to a three-dimensional vector. So let's take a look here real quick. Right now, what I have is I'm letting my c be 1. All right? I'm taking a vector v, which I picked to be the vector 3, 3, and I'm multiplying it by 1, and that gives me 3, 3. So it doesn't change, right? If I change my c here to 1.5, then I'm multiplying 3 and 3 here by 1.5, which gives me 4.5. And you can see on this picture what it's done, right? It's stretched it out. Oops. Yeah. I can change my value of v down here, but multiplying by 1.5 makes this black vector turn to the red one. If I multiply it times 2, it doubles its length, doesn't it? Okay. If I multiply it times 1/2, it's half the length. If I multiply it by -1, what does it do? Same length, right? Opposite direction. So these two vectors have the same length, just opposite directions. All right, now our first kind of definition when it comes to vectors. This is an important definition because it's a little different than the way we've thought of parallel in the past. Anytime we've talked about parallel lines, we've always said, okay, two lines are parallel what? If they never intersect, or they have the same slope, right? But they're distinct lines, they're not the same exact line, so they have different y-intercepts or something. Here we're defining what it means for vectors to be parallel. It's a little different. Two vectors are said to be parallel if they are scalar multiples of one another. All they have to be is scalar multiples. So going back to this right here, are these two vectors right here parallel? Yes, because they're scalar multiples of one another. In fact, this one right here is 1.75 times that, so it's a scalar multiple. But if that's the definition, then this vector is also parallel, isn't it? It points in the opposite direction, but it's a parallel vector because the definition says all you have to be is a scalar multiple. And this is a scalar multiple. The scalar is -1. Do you see the kind of the difference? All right, so that's what I put here. They could be pointed in opposite directions. By the way, little randomness. Two lines are parallel. We said if they don't intersect, right? That's a lot of people would agree with that. Okay, so I want you to check something out. I'm splitting my page into two different sections here. If anyone's taken like an art class or something, you go back and you look at through the history of art, or if you've ever been to like a museum or something, right? In the beginning, when people were drawing, you have to admit they kind of sucked at drawing, didn't they? I mean, think about like Egyptian drawings and, you know, cave drawings. I mean, they're kind of childish, aren't they? Little stick men and all back, you know, all sideways and stuff. And they weren't very good at getting that whole depth perception thing down, were they? So here's an example. I'm going to draw a street, looking down on a street. Okay, so someone tells me to draw a street. Here's a street. And there's a couple of buildings on each of the sides. Now what I'm doing to draw this is subconsciously I'm making some decisions. My road, I know my road, these lines are technically like parallel, right? So they shouldn't hit each other. And if my building's to the side of it, you know, these lines should also be parallel. So notice all my lines that shouldn't hit each other are parallel. And it's a decent representation of a street with some buildings on it. Very basic, though. I'm following Euclidean geometry. Euclidean geometry tells me two parallel lines cannot intersect, right? Well, what we realized later, as we were developing, our brains were developing, we were trying to understand how we could trick the eyeball, is we said we have to go to a different geometry. We can't use Euclidean geometry if we're going to make people see what we see when we're out in the street. So here's what we decided. We realized that to trick the eyeball, parallel lines actually will have to intersect. Just like when you're standing on a train track, you know we're always standing on a train track. And you look down train track, it appears to us as the train track comes together, right? So what I'm going to do is I'm going to make all the parallel lines on this, everything that was parallel, I'm going to make them all go to the same point in this new picture. So I'm going to draw what's called the horizon. And then for my art people or people who have done this before, we call this the what? No? I heard it, I think. Vanishing point? Is that what you said? Yeah, vanishing point. That's your vanishing point. So now every line that was written over here is going to have to go to that point. So here we go. There's my street, right? And then I'm going to be quick because I don't want to take too much time for this. there's one building. And notice that my blue lines here, it's not perfect, but I don't have a ruler and I'm doing this quick. My blue lines are going towards that vanishing point. And so once we realized that, then we started to understand how we could, you know, make our art look more realistic. But what we had to do is we had to violate, or not violate, we had to not use Euclidean geometry. So there's entire courses that you can take if you're like a math major called non-Euclidean geometry, where you learn all these different geometries, and so that you realize, I mean, this is like the fishbowl. We live in Euclidean geometry. Most math we do is Euclidean, but there's a whole different world of other geometries. In fact, for physics people, Einstein's theory of relativity is its own geometry. It's a non-Euclidean geometry. Yeah, am I done? Yeah, I'm done with that. Sorry, I try not to go off on tangents, but sometimes I think it's worth it. Here we go, magnitude of a vector. When we talk about the magnitude of a vector or the length of the vector, we're just saying how long is it, right? Tip to tail, measure it. And to do it in two-dimensional space, first we need notation. We put the good old-fashioned absolute value bars. That's what we use to represent the length. We put it around the vector, and then we do the square root. To compute it, we do the square root of each of the components, the sum of each of the components squared. And where does that come from? I mean, take a vector, right? To get to there, you've got this and this, basically. So you put them together, and you're trying to figure out how long this is, right? So you take this component and this component, you take square them and take square root. So it's just Pythagorean identity applied to a two-dimensional triangle. And then when you go to 3D, that's the same formula that we had like for that distance formula. So it just carries, it just follows through that you would add that last term into this. Right, so here again, a bunch of examples. I'm going to pick just one of these and do them because these are pretty, again, basic. I'm going to do example 4. I'll do, this must say, oh, no, it does say, okay, there's a glare. I'll do C and D here. Sound fair? And you can do the rest. So let's say we have a vector V is 2, 3, -5. Oh, whoa, okay. Can I go off on a quick little tangent again, real quick? Real fast, okay. Another non-Euclidean geometry. If I give you a triangle in Euclidean geometry, the sum of the angles should be what? 180, right? But that doesn't always apply to all geometric systems. For example, in what's called spherical geometry, where you're restricted to living on the surface of a sphere, kind of like on Earth, if I take a triangle on a sphere, it looks like this. So I'm going to go from the North Pole down to the equator. I'm just giving you one specific example. And then from the North Pole to another point on the equator. And then I'm going to come over across like this. That's a triangle on a sphere. And the sum of the angles of that triangle is greater than 180. It can't be 180. And maybe if I exaggerate this one a little bit, let me bring this one down like this. Let's say the center is in here like that. Let's say that that angle in here is 90 degrees. What's this angle right here? The one that goes from here down to here. What's that? Think about it. You've got this curve that's going up towards the North Pole, and then you have this curve around the equator. What's the angle between those two? It's 90. Now, you would have to actually look at the tangent to that line. So if I follow this tangent line coming down, right, it would be a vertical line. And then if I bring this one around like that, it would be like this. And then when you bring them together, the angle between them would be 90. But the same thing is happening. The same exact thing is happening here, right? So you're ready at 180. So then you always have to account for that one also. So in a spherical geometry, the sum of the angles of a triangle do not have to equal 180. I'm trying to give you, I guess, a what I called like the fish bowl idea. You know, a fish living in a bowl. That's a fish. You know, to the fish in a bowl, that's the world, right? That's their universe. That's everything to them. They don't realize that, you know, there's a table over here and a cat that wants to kill them and eat them, and, you know, there's whatever, everything else going on. So Euclidean geometry is its own fishbowl. What we have to understand is that there's a lot of other geometries out there that are more useful sometimes than Euclidean. All right, so what would, if I'm going to try and find 4v minus 3u, what I'm going to do is I'm going to write 4, and then I'm going to write the vector v, which is 2, 3, negative 5, then minus 3 times the vector u, which is negative 5, 7, negative 2. I realize that if this, at this point, this class is really just stuff you've seen, and it's not challenging, just bear with me. We'll get to something that'll interest you, hopefully, or at least challenge you. What should I do here? This 4 is a scalar multiple, right? It's a scalar, so I pass it through the vector like a distribution to each of the components and create this new vector, which is 8, 12, negative 20. And now my question to you is, what do I do here? Same thing. Now, do I distribute a 3 or a negative 3, or does it matter? I mean, okay, so if I distribute the negative 3 here, I'm going to put a plus here. If I distribute the 3 there, I'm going to have to keep the negative. So just make sure you keep track of that. I'm going to do a negative 3 and put a plus. So I'm going to go plus, 15, negative 21, 6. And now we're adding two vectors together. So we to add vectors, we add components. So I add 8 and 15. That gives me 23. I add 12 and negative 21, and that gives me negative 9. Negative 20 and 6 gives me negative 14. Do we all agree? So that's the answer to part C. Now part D, this was C, part D is the magnitude of 4v minus 3u. And so the magnitude, by definition, will be the square root of the sum of the components squared, or the sum of the square of the components. And that's going to be kind of a big number, so I'm not going to work it out, but you could work that out, right, on calculator if you needed to. And then I would either take the answer as the exact answer or the approximate answer. Normally on tests, I will usually try and direct you which way I want you to go. If I say exact, you just leave it as square root of whatever, right? If I say give me the approximate answer, then you would get in your calculator, take that square root, and give me a decimal, round it a few decimal places, and be done. All right, moving along. Now we talk about unit vectors. So any vector with length 1 is called a unit vector. If its length is 1, doesn't matter which way it's pointed, it's a unit vector. So I have a blue vector here, right? See that blue vector? And no matter which way I point that blue vector, I've got this little red vector tagging along with it, right? That red vector is a unit vector. It's pointed in the same direction as the blue one, but it's got a fixed radius of 1. You can kind of tell when I go around, right? It's hitting there at 1. Go around here, negative 1. And so that red vector is kind of stuck, the tip of it stuck on the unit circle as I move it around. What if the blue one is smaller? Well, even if I were to take that blue vector and make it shorter than 1, I still have a unit vector that points in the same direction, don't I? I think then the natural question would be, if someone gives you any vector in 2-dimensional or 3-dimensional space, so if someone gives you a blue vector, how can you find the red vector? So let's say I gave you a vector that was blue, and its length was 3. How would you get the red one? Scale it by 3, right? Or by 1/3. You would scale it back, so you would divide it by 3. What if you had a vector, its length was 10, and you wanted to figure out this vector that was unit length? You would divide it by 10, wouldn't you? So if I give you a vector in general, and I say, give me the vector that's pointing in the same direction with the unit length, or length 1, you would divide by what? Its own length, right? Whatever the length of that vector was, which is where this vector formula comes from. If someone gives you any vector, other than the 0 vector, we haven't talked about that, you can always find a unit vector pointing in the same direction by taking the vector. Now, this is important. This right here is a vector, isn't it? You take u and you divide it by what? Or the norm or the magnitude of u. The magnitude of u is a number, isn't it? So you're taking a vector and you're dividing it by a number, which is the same as scaling the vector, right? This is a number times the vector. So you're scaling the vector by the reciprocal of its length. So to do it, we just find the length and then divide each component by the length. So find a unit vector which points in the same direction as v. That's the next one I'll do. So v is 2, 3, negative 5. So in order to figure out a vector that points in the same direction as that one, I'm just going to need to scale it by the reciprocal of its length. So let's find its length. Its length is what here? 4, 9, 25. Right? So what's that? 38. You don't need to simplify that. You don't need to. In this class, if you have root 38, you can leave it. Root 12, leave it. I don't need you to pull out anything. Just okay. So all I'm going to do now is I'm going to take 1 over root 38 and multiply it times v, which was 2, 3, negative 5. Scale v by that, which just means each of the components gets divided. Everybody follow? We're done. That's the vector. Do you believe that that's a vector that points in the same direction that has unit length? How could I check it has unit length? Find its magnitude, right? Find the norm. So if I said, tell me how, what the length of that is, you would take the square root and you would do each of these squared, right? So you go that squared, what's this squared right here? 4 over 38 plus, then you go this one squared, which would be 9 over 38, and then you do negative 5 over this, you square it, and you get what, 25 over 38? They all have a common denominator of 38. Add them together. The numerators add up to be 38. 38 over 38 is 1. Square root of 1 is 1. We're done, right? That's just to confirm it. Remember that, okay? Because this will come up later. We will be in a totally different chapter, and we'll be like, oh, we need to find a vector that's pointing in the same direction, and that's what we do. Okay, now we get to what are called the standard basis vectors. Standard basis vectors in two-dimensional space. Anybody here taken linear algebra yet? Anybody? Linear algebra? Okay. You talked about basis vectors. Okay, so we have what here is called the standard basis vectors in R2. There are two important vectors in two-dimensional space, which we call the standard basis vectors in R2. They are, and they have special little symbols here. We say I hat and j hat. They are the vectors 1, 0 and the vector 0, 1. The reason they are so important is that, first of all, they are unit vectors, and every vector in R2 can be written as what we call a linear combination of these two vectors, as this illustration explains. Hopefully it explains it. So if I take this vector, u, I can make u by taking I. Now I is the vector 1, 0, so I points out this way, right? It's that vector. And j is the one 0, 1, points straight up. I can somehow put I and j together to get to the tip of that black one, can't I? I can add I and j's to get to that. And it doesn't matter what vector I pick, no matter where I am, like this one right here, I wouldn't take I, because here's I. I would actually take 2.385 times I, so that's a scalar multiple of I. I would add it to a scalar multiple of j. When you go tip to tail there, you would get out here. So when we say a linear combination of those two vectors, that's what we mean by linear combination. And that works for any vector that you have in two-dimensional space. Now, for linear algebra, again, people, if you haven't taken, don't worry. This is an orthonormal basis, meaning that not only are they a basis, they span all of R2, but they're orthonormal. Ortho meaning they're orthogonal vectors, meaning they're perpendicular, and orthonormal, normal meaning unit length. So there's even more restrictions on the standard basis vectors. I don't know if you saw that or remember that, but okay. Yep. In what? Statics? Yeah. The point I'm trying to make is that these are not the only basis vectors in R2. I could take this vector here, I'll call it R because my name's Robert, I'll call it R1. And I can take this vector here, I'll call it R2. Those two vectors also span R2. So if I come up with any vector in R2, I should be able to create that vector by some linear combination of these two. I can get to here by somehow pasting tip to tail and scaling by appropriate things to get to the tip of that red one. So those two vectors are also a basis. But the basis we're talking about here is called the standard basis, the one we use, the one we always like to use. Now in three-dimensional space, in order to be a basis or to span all of three-dimensional space, you need three vectors. You have I hat, j hat, which are just like the I and j from before, except they have a third component, right? So 1, 0, 0, j hat 0, 1, 0, and then k is 0, 0, 1. If you take those, and again, they're on orthonormal basis, you take all linear combinations, or you can span the entire space, three space, and every vector in R3 can be written as a linear combination of those two, or those three vectors. Now, as far as notation in this class, I do not use I, j, and k that often. I use it a little bit, but I always stick to the angled bracket for vectors. That's just the way that I've always done it, and so just be aware of that. Doesn't matter. I think everyone in this class should be comfortable with there's different notations. Like if I write here I plus j plus k, what vector is that in angled bracket notation? This is the vector 1, 1, 1. Now the reason why is because I is what? 1, 0, 0. J is 0, 1, 0. And k is 0, 0, 1. So when you add these together, you add their components, and you get 1, 1, 1. But there's also this notation. Anybody seen that used for vectors? It's a vertical notation for a vector, like a matrix. Yeah. So I think in all my time in math, I saw all three, and it just depended on the book and the author and what they wanted to use. And so when you're in physics, a lot of it's I, J, K, right? But when you're in a math class, most of the time they use angled brackets. Linear algebra books will use this vertical notation, but they all represent the same exact thing. All right. So I want to write V here as a linear combination of standard basis vectors. This is just to practice using ijk. That's all it is. But I'm going to take a little bit of time to do it. 2, 3, negative 5. So if I take the vector 2, 3, negative 5, let's all realize that that can be the vector 2, 0, 0, plus the vector 0, 3, 0, plus the vector 0, 0, negative 5. Everyone agree? Then I can say that that's equal to 2 times 1, 0, 0. I'm basically factoring out a scalar out of each of these to leave me with a 1 inside. I'll put negative 5 here. Right, so I pulled that, split it apart first, each component, and then I pulled out the scalar on each one, and then I know that this one right here is actually I hat, right? This one right here is J hat, and this one right here is K hat. Yeah, I mean, you wouldn't, I'm just showing you this. It's, I mean, technically, if I said, hey, write that in IJK, you know, you just write it this way. But I'm just trying to make sure everyone's comfortable with why it is that way, you know. Look at the question, though. Look what it's asking, though. Rewrite V, right, here's V, as a linear combination of the standard basis vectors. So I have rewritten this vector as a linear combination, meaning scalars times my basis vectors, linear combination, addition, subtraction between them. So that is it right there. That's it? We're done? No, we can't be done, are we? Oh, okay. 10.2 is done. Homework for 10.2. I'm not sure what page it is, but it's number 5, 15, 17 through 21. I'm sorry? Yes, I don't have the page numbers. Anyone have the page? 515? Oh, sorry. 5. What is it? 5 what? 549. But it's from 10.2. All right, that's the big thing. You're going to notice, especially when we get to the notes for the next section, as you go through, at the end of the section, sometimes I give you a page number and a homework assignment. That's for the first edition of this book. So it does not match up with what you have. So I will always tell you what the homework problems are when we get to the end of the section. Don't go off of what's in those notes because they're incorrect. Sometimes they're right, but they're the wrong page. So that's right. Yeah, exactly. Someone's got to make money, right? Yes. Oh, we'll have 2. We'll probably finish 10.3 today. My intention is to finish 10.3. We'll see how far we get. Yep. All right, so now we move on. Close this down. Is this going okay for everyone? Does this seem like this is going to work with the way it's being presented and not putting you to sleep? Yes. How do I? How do you? Oh, the printer that I had here at work? Yeah. Yeah. Yeah, I know. That's why I was saying if you want to bring your computer, do you have a laptop or something you can bring? If you want, if not, you can just follow along. Just be ready to write things down. You know. Yeah. Yeah, I'm not trying to make this like a printing class, you know, where that's like a, but the problem is it's too many students to, I've done it in the past where I actually provide it all, and in the summer I had in my Cal 3 class, I provided the bound copy for everyone, but I had to make them myself. So I'm sitting there and I'm printing them all out, and I'm using the machine to do that thing and punch the holes and run the little binding through. It's just too much for me. So, but you have an electronic copy. Yeah, yeah. So I don't recommend you print it. It's a lot of paper. It's a lot. All right, so far right now, we have vectors in 2- and 3-dimensional space. We know how to add and subtract two vectors, and we know how to scale a vector, scalar multiplication. What we don't know how to do is multiply two vectors. Just like with numbers, right? Numbers, you can add two numbers, subtract two numbers, but multiplication of numbers makes sense to us. Multiplication of vectors, there really isn't technically a multiplication of vectors. There's two different ones that we have for vectors. There's called the dot product and the cross product. And so what we're going to start with 10.3 is the dot product, and then after we finish that, we'll move on to the cross product. So dot product is our first definition for vector multiplication. Vector on vector. Given two vectors in 2-dimensional space, we define a new product between them as follows. Here's V, here's U. If we take U and we put this dot between them, it's kind of like a bolded dot. If we say U dot V, then what we're doing is we're taking the first component of V, multiplying it times the first component of U, and then we're adding to that the second component of V times the second component of U. So you're multiplying components and adding them together. So the dot product is the sum of the products of the components. It's vital to notice the dot product yields a number. Okay, when you take the dot product of two vectors, you get a number. So this is kind of different than things, a lot of things that you see in math. When you start out grade school, right, whenever you start with numbers, right, you add them together, you get numbers. You subtract, you get a new number. You divide, you multiply, you get numbers. So numbers work, you know, do arithmetic on numbers, you get numbers. If you have functions, you add them together, you get a new function. You subtract them, you get a new function, right? You take a function, you integrate it, you get another function, right? You differentiate, you get another function. Here with vectors, we get two vectors, and we have an operation where we multiply them together to do this dot product, and it spits out something that's not a vector anymore. It's a number. So that's just something to keep in mind. It happens in math. We just need to kind of see that it's happening. I just don't want it to kind of get under the rug and we don't notice it. So we have a number. Also notice we use the bolded dot. If we are in 3-dimensional space, our vectors have 3 components. So now we multiply the components, all 3 components, and add them together. Again, the answer is a number. U dot V. Can we just say what U dot V would be here? Like slowly say it? It would be 2 times -3, which is -6, plus -12 plus 35. Add those all up. That's your dot product. Right? Do I need to do it, or? So some properties of dot products. If I take a vector U and I dot it with itself, then that means I'm doing U1, U1, plus U2, U2, plus U3, U3. And that is equal to the magnitude of U squared. Why? Why is that? Why is that equal to this? What is the magnitude of U? What is the magnitude of a vector? It's the sum of each of the components squared, right? So I take U1 squared plus U2 squared plus U3 squared. Isn't that what the magnitude is? And then what happens if I come in and I square it? Well, that means I square this, right? And the square root goes away, basically. And I'm left with u1 squared plus u2 squared plus u3 squared. But isn't that what this is? Yeah. So when you dot u with itself, you get the magnitude of the vector squared. Make sense? All right.
So when you use dot product, aside from that, of course, that number that you get has nothing to do with the magnitude?
Stay tuned. We have the geometry of it all is about to come, but let's just get the mechanical part of it first. This property says if I dot u and v, it doesn't matter which order I go in. And that's because multiplication is commutative, so commutative doesn't matter. And then we have the distributive property over addition. So if I take two vectors and add them, and then dot that new vector with u, I could have, if I wanted to, dot the u and the v, then dot the u and the w, and put those two answers together through addition. This one right here, scalar multiplication. Scalars can move through the dot product. So if I'm going to scale a vector, then dot it with something, I could move that scalar over to the other one. Or I could move it out completely. Dot them first, then scale. So all those properties hold. And then the last one, the zero vector dotted with v is always, what? The zero vector dotted with v is the number 0. The number 0. Yeah. But again, it's two vectors become a number through this operation. So it's spitting out something that's, it's like two cats getting together and, you know, a couple of months later, they have a dog. You know, it just doesn't work that way, right? So it's kind of odd, but it is what it is. All right, I guess I can do this one. If you were to do this one, let's just talk about the different things you could do. Let's not actually work with it. Let's just talk about the different things you could do with this, using some of those properties. You tell me whether or not this would be okay. If I have 3u dotted with v plus w, could I do this? 3u dot v plus 3u dot w. Could I do that? Yes, because you can distribute dot product over addition. Could I do, how about this? Would this work? Not 3u dot 3v plus w. No, that wouldn't work, right? The 3 would have to be where? On both of them, right? So that's no go. Trying to think of some other combinations. You could do just wait on the 3, right? And go u dot v plus u dot w. You could do that. Agreed? Leave the 3 there, pass this through, and then scale it all at the end. How about this? This separate sort of idea here. If I have u dot v dot w, is this equal to u dot v dot u dot w? Like, do you distribute this through dot and then dot? It's only distribution over what? Through addition, over addition, right? So this would be a no-go. What you have to realize here is that v dot w is a scalar, isn't it? When you dot these two vectors together, it's a number. So this is just a scalar times u. That's all it is. So could I do this? Think you can move parentheses like that? Anyone know what that property is called when you move parentheses around? associative property of the dot product. Now, is that in your list of properties that I gave you? Is the associative property here? This is kind of like it, right? But this was with the scalar, wasn't it? So I haven't given this property to you. It makes sense that it would work that way, but you would have to prove it's true. I'll leave it to you as an exercise. Let's make that a little bonus, okay? Everyone likes bonuses. Just prove whether or not the dot product is associative with 3 vectors. So you'd have to show that this is equal to this, right? Those two are the same. And you have to do it in general. So like take a vector, call it U. U is the vector U1, 2, 1. U1, U2, U3. Take a vector V, which is V1, V2, V3. Take a vector W, which is W1, W2, W3. And just start doing these and see if you can manipulate it to turn this into this. Bonus, you just turn in next class. It's not a bonus because it's hard. It's just a bonus because it's something that really we don't have to do. All right? All right, now moving along. The dot product theorem. This is a huge result. Okay, it's one of our first main big results here. If theta is the angle between 2 vectors u and v, then the following is true. U dot v equals the magnitude of u times the magnitude of v times cosine of the angle between them. So you're asking, like, you know, what is the relationship, kind of like what geometrically is happening? So the dot product of 2 vectors gives you a number, right? That number can be found by taking the magnitude of u times the magnitude of v, so their lengths, times cosine of the angle between them. So if that's, I'm not here to show you that that's true. I'm just here to supply that to you, all right? We can show it's true other ways, but not going to. The results of this theorem. Okay, so what does this theorem tell us? If we have 2 vectors, and the angle between them must be between 0 and pi. Why is that true? Yeah. So let's say I have 2 vectors, right, like this. To talk about the angle between them, I want to put them tail to tail, not tip to tail, tail to tail. And I want to measure the angle between those two, all right? Why is that angle between those two have to be between 0 and pi? Well, they're 0, right, which means that they would be parallel vectors, right? And now if I increase the angle and I get to pi, it's pointed in the opposite direction. They're still parallel, right? And now if I go past bigger than pi over 2, then the angle between them is now this one. Right, so we don't talk about the larger one, we always talk about the smaller one. Make sense? So we always have to have that restriction between 0 and pi. And now let's talk a little bit about what happens to cosine, right? What happens to the cosine function? Because cosine is in here, right? In this formula. What happens when the angle is 0? So your angle is 0, right? That's the angle between the vectors, so they are pointed in the exact same direction. If your angle is 0, what's cosine? Cosine is 1, right? That means the formula becomes magnitude of u times magnitude of v, cosine of 0 is 1, which just gives you the magnitudes. So if I have 2 vectors that point in the same direction, right? And I say, I compute the dot product. What does that dot product represent? The product of their magnitudes, right? It's the magnitude of this one, its length, times the magnitude of this one, right? That's what it represents. Now, what if the angle between them is pi over 2, 90 degrees? What's cosine of 90 degrees? Cosine of pi over 2 is 0, right? Which means that cosine of pi over 2 is 0, which means that the lengths don't matter anymore, right? because this is all 0. And this is, again, this is one of the biggest points I can make in this section. Two vectors are perpendicular, orthogonal is another word we'll use, if and only if their dot product is 0. This is a way we can check if two vectors are perpendicular or not. We take the dot product. It has to be 0 for us to say they're perpendicular. That's what this says right here. This is the big result. U and V are orthogonal vectors, perpendicular vectors, if and only if U dot V equals 0. What does if and only if mean? Yeah, this is a logic thing. Okay, if x equals 4, then x squared equals 16. Agree? Can you say it the other way around? If x squared equals 16, then is x equal to 4? Not always. Could be, right? Could have also been negative 4. Right? So this statement works in one direction but does not work in the other direction. Right? So I could not write this. X equals 4 if and only if. Sometimes we write IFF instead of if and only if. X squared equals 16. This would not be valid in mathematics, because when you have an if and only if, what it means is this means that has to be true, and the other way has to happen also. This means that has to be true. So this is a very, very strong statement right here that we're looking at. Because it says, look, if you know they're orthogonal, okay? If they are orthogonal, the dot product has to be 0. And the other direction says, if the dot product is 0, they have to be orthogonal. So it goes both directions. Very strong, strong statement. Not every mathematical statement is an if and only if statement. All right, now if the angle is between 0 and pi over 2, so if the angle is anywhere between 0 and pi over 2, we know that, well, I'll do it this way, because when we think about unit circle and angles 0 to pi over 2, we know that anywhere in here cosine is positive, isn't it? Cosine is positive. So since that's a positive number, and the magnitude of two vectors or their lengths should be positive, that whole thing has to be positive, right? So if my dot product turns out to be positive, I know that the angle between these two vectors is smaller than 90 degrees. Now, on the other hand, if the angle between the two vectors is between pi over 2 and pi, I know cosine over there is negative, which means we have a negative number here, which means the dot product will be negative. So this is just a little thing I made up where I can get two vectors and I can drag them around. And so notice right now these two vectors, the angle between them, right, is smaller than 90, or yeah, smaller than 90 degrees. So it's giving me, I'm having the computer compute the dot product, and it's coming out to be 6.44. And so it's a positive number, right? If I drag it up here and I make them, well, let me put it right on top. When I put it right on top, that dot product represents the what? The magnitudes, right? The product of their magnitudes. But if I drag this thing over here to where I get to about 90 degrees, you saw it right in there. It switched from positive to negative. And if I get them perfectly orthogonal, it should get 0. It should be 0. I can't do it because it's just impossible for me to drag right to 0, to 90 degrees. What is this? Oh. I'll let you do this on your own because this one, again, is trivial. I want you to find the dot product of these two vectors. I give you the lengths and I give you the angle. So this is just the length of these two multiplied, so that's 21 times cosine of 31. To make sure you're in degree mode, multiply, you're done. Are these two vectors orthogonal? The only way they can be orthogonal is what? If what zero? Dot product, right? What's the dot product of these two vectors? 3. So 2, 4, dotted with 6, -3. So when I dot, I do these two multiplied, which is 12. I add to that these two multiplied, which is -12. What's that? 0. Did I write down the problem correctly? Okay. So are they orthogonal or not? Yes, they are orthogonal. Ten three, example 5. Find the A such that these are orthogonal vectors. Find the value of A that makes these two orthogonal. So what do we need for these to be orthogonal? We need the dot product to be 0, right? So let's see what we can do to make that happen. This is a new problem. I want 2, -2, 6, dotted with A, 3A, -2A to be equal to 0, right? That's what I would like. So go ahead and dot these out. 2 times A is 2A. -2 times that is -6A. 6 times that is -12A equals 0. Correct? So what do we get? -16A equals 0, which means A must be 0, which means what? Well, you can use, both formulas are interchangeable. Like, if you're trying to find the dot product of two vectors and you're given the components, this is what you use. If you're given their lengths and the angle, then you use the other one. What is this saying to us? That this vector has to be the 0 vector, right? So we were trying to find the A that would make these two vectors orthogonal. The only A that worked was 0, which means the only way we can make this happen is if we dot it with the 0 vector. Does that mean that there is no vector that is orthogonal to this vector? Is that what this is saying? That's not what we're saying. We're saying there's no vector of that form where it's some number, then some number times 3, then some number times -2. There's no vector of that format that works, that is orthogonal to that other vector. Of course, if I have a vector in three-dimensional space, the vector 2, -2, 6, there's vectors orthogonal to that, right? I mean, look at this one right here, right? That's orthogonal. And if I spin this around like this, every vector there is orthogonal, right? So you could almost say every vector that lives on that plane is orthogonal, right? So there's infinitely many that are orthogonal, but no vectors that look like that format would work, except the 0 vector. Dot product theorem, further results. This is just another formula, but it's actually the same exact formula we just had, solved for theta. So if you take that formula before, you take the two magnitudes, divide them through on both sides, and then take arc cosine on both sides, you get this. But what's convenient about this formula is that it gives you a way to find the angle between two vectors if all you have are the vectors. You would have to dot the two vectors and then divide by each of their lengths and then do an arc cosine on your calculator. So how do you find the angle between those two? So if I have the vector 2, 4, 4, and I have the vector negative 3, 7, 1, and I want to know the angle between them. So those are vectors in three-dimensional space. If I attach tail to tail, there's some angle between them. I'm trying to figure out what it is. So I'm going to need to use the formula. Theta is arc cosine u dot v over magnitude of u times magnitude of v. So let me go ahead and on the side work this out. What's u dot v? Negative 6 plus 28 plus 4. Yes? So 26. All right, I need the magnitude of u. What's the magnitude of u? Square root of 4 plus 16 plus 16. 2. Is that 36? So 6 is the magnitude of u, and v, the magnitude is, what do we have? 59? Root 59? So now what I'm going to do is come over here and say theta is equal to arc cosine of u dot v, which is 26 over 6 root 59. And then break my calculator out and I'm going to compute it. Well, actually, I'm not going to. You're going to. And then you got to just make sure that you understand what mode you're in so that when you write your answer, you either tell me degree or radians, right? Well, you don't have to say radians, right? You don't, if it's degrees, you need to put the symbol. If it's in radians, you don't have to put the unit. Anyone want to provide an answer here? Greater than 0, less than infinity? Something like that? Greater than 0, less than pi. Degrees or radians? 55.7. Anybody else try it and get the same thing? No? Same thing? Okay. If two people agree, then we agree. Okay, are these vectors orthogonal, parallel, or neither? Let's start with orthogonal. How could you check to see if they're orthogonal? What's that? Dot product and see if it's 0, right? Okay, so if I want to know if these are orthogonal, dot them out, see if I get 0. So let's dot them mentally. 2 times negative 4 is negative 8. Negative 2 and 4 is negative 8. And then 6 and negative 12 is negative something. And that's a bunch of negatives, and they all add up. It's still negative, not 0. So it's definitely not 0, so they're definitely not orthogonal. Okay, are they parallel? How do I check if they're parallel? What does it mean for two vectors to be parallel? They are scalar multiples. How can you tell if they're scalar multiples? Yeah, in this case, it's pretty easy. But there's a way to check that if you can't tell really easily. You could do that, but there's an even easier way. If where are the vectors? If I have 2, negative 2, 6, and I have negative 4, 4, negative 12, if they're scalar multiples, then there's some number that I can multiply times the first one to get the second one, right? Scale, which means that there's a common ratio between the components. So let me do this. Let me just take each component and make a ratio. So I'm going to do this component and divide it by that component. What would happen? 2 over negative 4, I get negative 1/2. Okay, do the same thing here and here. What do you get? Negative 2 over positive 4, you get negative 1/2. And then take 6 and divide it by negative 12, and you get negative 1/2. They all have a common ratio, which means there is a number that turns each one into the other. It's a common, they all have that common ratio. It's kind of like similar triangles almost. So since they all have a common ratio, they are parallel. Now you can tell by this what it is. If I multiply this by negative 2, right? Negative 2 turns into this, negative 2, that, negative 2, that. But if it's not so easy to see, you can do this. All right, the vertices or the corner points of a triangle in three-dimensional space are given. Is this a right triangle? So we have 3 points. So let's say we had that speaker there, and then we had the bottle here, and then we had the doorknob over there. That creates this triangle. Is it a right triangle? How can you tell? What does it mean to be a right triangle? In Euclidean geometry, what's a right triangle got to have? You have to have a 90-degree angle, right? Which means that, how can I check from this bottle to there, to the speaker and to the doorknob, how can I check if this is a 90-degree angle? They have to be perpendicular, yes. So how could I check to see if it was perpendicular? If the dot product is 0, right? The dot product of what, though? This is the big key here. The dot product of what? Those two what? Okay, but I didn't give you vectors, right? I gave you points, didn't I? So what I have to do first is I have to say, look, from this point, my bottle, to that speaker, I need to create a vector. And then from this bottle to the doorknob, I need to create a vector. We can create vectors from points. We did this last class in the very, very beginning. If I give you 2 points, the vector between them is, we compute it. So the biggest mistake I see on this is that people start dotting the coordinate points. You don't dot the points. You can't dot points. You dot vectors. So I have to create the vector from here to here, from here to here, and then I can dot them and hope for 0. If I don't get 0, what? Not yet. Now I have to go and I get to stand up there at that speaker and look at the vector coming from here to here and from there to the doorknob and then dot those. And if that's not 90, or if that's dot product's not 0, I've got to try one more. I've got to go from there, here, and there, there. You're going to have to come up with 3 sets of vectors and dot all 3 and check for 0. So here's how I'm going to do it. Because this is in 3-dimensional space and I don't feel like drawing 3-dimensional space, it would be too hard. I'm just going to label the points arbitrarily. So just imagine this is in 3-dimensional space. I don't know if it's a right triangle, so I'm going to draw it like it's not. Wow. There we go. Let's look at this first angle right here. I don't know. I'm going to call it theta. I'd like to know whether or not theta is going to be 90. And we'll call this what? Beta over here and maybe alpha over here, something like that. Let's check theta first. So to check theta, I have to create 2 vectors. The vector that would go from 2, 0, 4 up to 1, negative 3, negative 2. And then I have to look at this vector over here that would go from 2, 0, 4 over to negative 6, negative 2, negative 5. So what is this vector here? How do you do it? You subtract one by the other. Now what order do you go in? Do I go 2, take away 1, 0, take away negative 3, 4 take away negative 2, or do I go 1 take away 2, negative 3 take away 0, negative 2 take away 4? It depends on which way you're going, right? I'm going from 2, 0, 4 to the 1, negative 3, negative 2. So I will go 1 take away 2. So that gives me negative 1. And then I go negative 3 take away 0. And then I do negative 2 take away 4, so negative 6. Everyone agree that's the vector? And then I'll do the same thing over here to get this vector. So what do we have here? Negative 8, negative 2, negative 9. And now let me dot them. If I take negative 1, negative 3, negative 6, and I dot it with negative 8, negative 2, negative 9, can that be 0? It can't. Look, all the components are negative, aren't they? So when you multiply these two, it's a positive number plus positive number plus positive number. There's no way that's ever 0. So I don't even have to compute it. It's not 0, which means that theta is not pi over 2, which means it's not a right triangle. No, that means that angle is not 90. So now what you would do is you'd set up the others and create new vectors. I'm not going to go through that, but you understand what you would have to do. All right. Vector projections. How are we doing on time? Wow, we're almost out of time. This is probably a good point to take a little, or take a break. Take a little break. Take a break. Damn, we didn't quite get to the end here. I've got your first take-home quiz. Let me hand this out. Mind passing those over? Got any extras? I'll take them. Let's take a quick look at this. You must show all steps and justify all answers. Do all work on separate paper. So I don't want you writing on this and cramming all your work on here, okay? You must, your work must be neat, in order, and stapled. Not folded with that weird thing that people do. Stapled, all right? Box your final answers if applicable. I mean, sometimes you can't box them, but if it makes sense to box an answer, box it. All these problems should be done using concepts from 10.1 to 10.3. We haven't quite done all of that yet. So let me show you what you need to do, or what you can do. Number 1, you can do number 1, but I have to put something on here to make sure everyone's on the same page with this. The way this is drawn, I'm going to add one little thing to it to clear up any possible confusion. This is a right angle right here. I'm going to read that problem one time. I'm going to stress a word when I read it. If U and V are unit vectors on this regular pentagon, then find the following. Your answers should be numerical quantities. Your answers should be numbers. There's going to be numerical answers for this problem. Numerical answers. Number 2, find the value or values of B, which makes these vectors, whoa, that's all bad, which makes these vectors orthogonal. It's supposed to be vectors. Do this by hand. In other words, you are not allowed to use a calculator or a computer or anything else to try and help you solve the equation you're going to be looking at. Because when you do try and figure out what makes those dots a zero, the equation is going to be something pretty ugly. I want to see if you remember how to solve that sort of equation by hand. My hint to you is the rational zero test, which is a huge hint. Number 3, a parallelepiped has these corners. So the picture is there. Find the following: the length of the diagonal, the angle between the vectors, the volume of the solid. Okay, I've not covered the volume, so you can skip part C. And then on number 4, I have not done number 4, surface area of a tetrahedron. So we can skip number 4. Would you like me to offer 3C and 4 for bonus? Okay, I'll offer 3C and 4 for bonus. What I ask you to do, though, if you're going to do 3C and 4 for bonus, it must be turned in on a separate piece of paper titled bonus for quiz 1 with your name, so separated. That way I can distinguish things. Does this sound reasonable? If you have any questions on how to do something, like especially number 1, if you're just not sure about something, don't make an assumption. Just call me or text me, email me, say, hey, can I assume this or something? You know, I would hate for you to go and work through it and you assume something you couldn't. Anything else? Anything else? Homework out of that section. We haven't covered all the problems in 10.3. At the end of the notes, I'll just tell you this. At the end of the notes, they give you an assignment. That is the correct assignment. It's the wrong page. It's page 556. So if you wanted to, you could start working on that assignment. You just won't be able to get through all of it because we haven't covered all of it yet.
The other homework was 10.2, right?
It was 10.2. That's 10.3. I need it. Sorry, I know you want to go. I'm just going to call your name real quick to make sure you're here. Joel, Jose A, Angel, Diego, Jason Bali, Adrian Castillo, Allison Cook, Mark Cortez, Matthew Crenwelch, no, Jamie. Nope. Jaime? No. Jamie Garza? Thomas? Hernandez, yes. Okay, Joshua, both Joshes? Okay. You can go when I call you. Gerardo? Raul? Jose Rojas? Christopher Schaefer? Tamara? Did I say that right? Terima? Okay, I'll try. Okay, let me try Daniel. And Alexandria, of course, you're here. Did I miss anybody? Called everyone? Pardon me? Daniel Patrick, yes. Okay, so I do not have Jason Bali, Allison Cook, Matthew, Jamie, Gerardo, Christopher Schaefer. Okay. I'm still recording that crap.